Okay, so in this version of acids and bases, we have acids. An acid is something that gives a proton, or H+, which we'll have a look at in a minute. They are the same thing, which I'll show you shortly. And a base is something that accepts or receives a proton or a hydrogen ion, a H+ ion. Okay. And these things come in pairs. An acid and a base go together. One gives a proton or a hydrogen ion, and the other takes a proton or a hydrogen ion. So there's no creation of matter or loss of matter or anything like that. There's simply transfer. And here what we're doing is we're transferring a positive ion from the acid to the base. Now that's interesting because later on we talk about transferring negative charge, and that's your other type of reaction, which is electron reactions. This is basically a proton reaction. Anyway, before we go any further, let's have a look at how that happens. Now, if we look at the first chemical reaction on page 365 of the book there, what we get is HCl, gas, plus water, liquid, goes to Cl minus aqueous there, and H3O plus, also aqueous. And what we can see here is that the hydrogen has lost its electron here to become H+. That extra electron has been left with the chlorine to give it an overall negative charge. I'll explain that in a minute. And that has then become attached to the water molecule, which has turned into this here. All right. So you can see here also, just before we go into this detail here, that on the reactant side here, we have a net charge of 0 because neither the HCl nor the H2O are charged. And over here on the product side, we have -1 and +1, which gives a total overall charge of 0. So there's no change in overall charge on either side of the arrow. It stays the same. It's simply shuffling from one reactant to the other reactant to form the products there. All right, so let's have a little bit of a look at the HCl here and see what's happening, what it looks like first in electron dot form. Okay, so hydrogen has 1 electron and chlorine has 7 electrons in its outer shell, like this. And so HCl is a covalently bonded compound. The chlorine, if we just look at the chlorine, if I take, for example, if I cover over the hydrogen, we can see that the chlorine has 8 electrons and a full outer shell. And if I cover up the chlorine, we can see that hydrogen has a full outer shell of 2 electrons, and that's fine. That's why it's formed a covalent bond. Now, the electrons in this pair that are joining the hydrogen and the chlorine are not evenly distributed. And this comes back to the concept of electronegativity, which we've already talked about quite a lot. And we can see that 2.1 is the electronegativity value for hydrogen. And for chlorine, it's roughly 3.2, a little bit less. Now, you don't need to know those off the top of your head. I mean, I know the hydrogen one, but I had to look up the chlorine one, so that's fine. So if, for example, we had a hydrogen just bonding with a hydrogen, and they were both even, the electronegativities are the same, 2.1, 2.1 there, then we could view that pair of electrons there as behaving like a cloud, because they don't stay still. They move around very, very fast, and so we can draw, like they're where they probably are, as like a cloud area. And because the electronegativities are the same, they would spend their time, each electron will spend its time roughly half the time around this hydrogen, roughly half the time around that hydrogen, and that's fine. And so both of them do that, and so the distribution of electrons is even between the two. However, when we have the 2.1 versus 3.2 here, that's not a linear difference, that's an exponential difference. And so this has a much greater pull on those two electrons than the hydrogen does. So instead of looking like this, what it looks like is that the chlorine is hogging the electrons like this. And the electrons in that pair are spending almost none of their time around the hydrogen. And that's where we get the idea of the partial positive charge, which is a very large partial positive charge because of the difference in electronegativities. And in fact, the bigger the difference in electronegativities, the bigger the partial charge on the hydrogen will be. And you'd be thinking, well, surely that means that there's a partial negative charge on the chlorine too, and you would be correct. Now, what that means is that the hydrogen is basically just hanging on by a thread. If something else comes along, like a water molecule, which I will pop in here, let's put it in this form here. And of course, water, we know, has two lone pairs sticking out of the molecule. And these both have a very strong negative charge on them because they're just a pair of electrons there. So it's got this whole negative region here. It's got a positive region here and a negative region here. And in fact, what happens when the water molecule comes along is that there's a very good chance, not 100%, but a very good chance that that hydrogen nucleus is going to detach and leave those two electrons there and come off as a H plus ion because it's lost its outer shell electron, and it's going to be attracted because it's positively charged to this here, and it's going to plonk itself on one of the lone pairs which have the negative charge. And that's where this H3O plus comes from. You can see here that this is no longer the same as the water molecule before the hydrogen ion went onto it. It's got 1, 2, 3 hydrogens, 1 oxygen there. And before the hydrogen came on, it was neutral, no overall charge. Even though it's got charged regions, it has no overall charge. But the proton that went onto it does have a positive charge, and so it's increased the overall charge of the molecule by 1. So that's where your H3O plus ion, this thing here, comes from. It's called a hydronium ion. Not sure if you need to know that. And of course, we've got the chlorine here, which has now got its full outer shell. It's happy. This here, is it stable? Not particularly. The hydrogen is happier being on the water molecule than it was with the chlorine, but it's still not particularly stable, and this will react with stuff. Now, that's actually the hydrogen ion in solution, and that's the thing, that's the form in which acids react. When you put HCl into water, all of these molecules break down and turn into these here.